Now it looks like we're on there. We're having a little technical difficulty there, folks.
And I guess just to double check, what are you seeing, Scott? The wearable state of the market screen?
Yes, we are.
And do I need to repeat this, or did we just lose the live connection just now?
I would start from right here and go ahead. So I apologize for anyone that may have heard this, but we were having a little bit of a technical difficulty. So go ahead, Mark.
Okay, I'll do it even more quickly. Bottom line is the wearable market's growing. That's all we wanted to convey here. And third parties certainly agree with that assessment. And a couple of the big areas of growth are the general CE wearables, like a general smartwatch, and definitely medical, healthy lifestyle types of wearables, not just smartwatch form factors, but other interesting form factors which are popping up left and right, from earbud type products, but are also doing medical monitoring, to arm and leg smart sleeves that are wireless connected and doing medical or healthy lifestyle types of monitoring. So it's a good industry to be in. There's a lot of growth. There's a lot of new entrants, a lot of activity. So how's Hirose trying to support our customers in this market? Well, one thing that's worth noting is that we're a little different from most of our competitors in that we are a pure play connector supplier. What's that mean? It means all of these sites I'm showing here, all of our factories are really dedicated at just serving you, our end customers. We don't have any internal customer conflicts. We don't have any competing product lines where we need to allocate our factory lines for other purposes. And we don't have any downstream businesses or resource conflicts. And this has proven to be, I think, an advantage for us in doing things like managing the recent supply line issues over the pandemic and even the post-pandemic tail that has caused a lot of those issues. We didn't come through unscathed, but I think we came through significantly in better shape, and in better shape to keep supporting our customers than many others. We have factories across Asia. Next, let's just clarify what types of wearable products we think about when we're talking about supporting wearables. Again, the smartwatch is probably the best, sort of core example of a mainstream wearable product today. The types of connectivity that exist within a even small product like a smartwatch are manyfold, including connectors to route signals to displays or sensors. Those could be simple sensors, or they could be large, higher definition devices like touchscreens. There could be small subboards, small sub-modules inside a small product like a smartwatch that need connectorization solutions. There can be power paths, or certainly going to be power paths inside this type of product, routing that current from the battery, or when it's in a docking station, from a line power to those internal components. There can be wireless connectivity, and there's going to be some sort of I/O often, even in these smaller devices. So these are all areas where we have different solutions that are really focused on giving state-of-the-art technology to our customers doing these types of products. Another example of a wearable product would be another pretty obvious one, VR, or in this case, an AR type of glasses product, which can have an even more demanding form factor in terms of thin outer packaging and longer extent of needing to route signals from one side of the product to the other. A lot of the similar types of connectivity are going to exist within a VR or AR product as in something like the just shown smartwatch. And if we go to sort of the end of the spectrum on size down to something as small as earbuds, and I'm still sort of amazed that, something as tiny as an earbud still can have multiple connectors inside it. And that's because there's multiple little tiny substrates or individual componentized elements within these products that need to be connected to each other. So you might find multiple areas. And shown in the upper left there is something else worth noting. Many wearables also include accessories, a docking station, a charging case, and those bring their own connectorization requirements and are going to be maybe a little bit, larger form factor options and I/O devices as well. And of course, there's a lot of other form factors that are evolving. So the wearable is an interesting space, as I mentioned earlier. We're seeing a lot of things down to a finger ring, that has actually complicated circuitry built into the ring. And by the way, connectors as well. And on the larger scale to a lot of wearable products that are aimed more at other parts of the body for wearing and giving some benefits. Next, let's clarify the types of connectors before we just dive in and start giving you our view of how we're trying to support wearable industry. What do we mean here at Hirose when we're talking about connectors, and what types at a very high level are we talking about? What covers probably the biggest breadth of our product line and the biggest breadth of what our wearable customers are interested in are what are often called board-to-board connectors. These are little tiny connectors. They can be used in a true board-to-board configuration to sandwich two PCB boards together, but much more often today, our customers are using these little surface mount connectors and surface mounting one onto a small PCB, but the other half onto a flexible printed circuit cable or an FPC cable. So when you see board-to-board and you're talking about small consumer electronics types products, you can almost think of those more as a board to FPC type of solution, although they can be used for either. The next biggest category that covers a whole lot of products is the ZIF, which stands for Zero Insertion Force. Zero insertion force connectors are in a way simpler. They're a single element. They don't have two mating parts, but a single element. And the other mating element is simply the FPC itself, which slides right into the connector and then is either latched with a manual actuator or plastic lever built into that connector piece itself. Or more recently, we've introduced versions of ZIF connectors which automatically lock. And we'll come back and give you a few more details on those. Another high-level category of connectors, of course, are I/O interface connectors. We do a big lineup of micro USB connectors, which are still used broadly across products such as wearables. But just or more interestingly is the proliferation ongoing of USB Type-C. And we have a pretty broad and growing lineup of Type-C receptacles, plugs, and cables as well. And we'll talk about those just very briefly. A next large category of connectors is board-to-wire. These are sort of self-explanatory, and at first blush, they may appear, something more of an industrial nature and too big to use in something like a wearable. But again, we're Hirose, and we do these down into sub-millimeter dimensions in terms of the height from the surface to the top. So these can actually get down to a size which can easily be accommodated inside of at least certain wearable types of products. And you really can't beat a board-to-wire for physical flexibility, literal physical flexibility for routing in 3 dimensions. You can obviously take these discrete, very small gauge wires and route those in any direction they need to go, which isn't really true for most other types of cabling solutions. And finally, we analog RF for wireless connectivity is another big requirement, and we have both individual microcoaxial cables with bonded, soldered, or crimped plug connectors on the ends of those, which go to very small, for instance, 2 by 2 millimeter little surface mount receptacles that can be placed anywhere on a small PCB. So these are great for routing to a Wi-Fi or Bluetooth antenna if you have something like that. And we also have ganged versions of the microcoax for more parallel high-frequency application, such as display interfaces, which aren't analog. They're a differential digital signaling protocol, such as MIPI, for example. But engineers are often deciding that they want to have better shielding for their high-frequency display or sensor interfaces, and a ganged microcoax is a good option to consider for that. So those are some high-level categorizations, just sort of a quick primer on the types of connectors we're talking about. So let's just jump right into three actually design challenges that we're spending a lot of time with our customers trying to help them address. And the first here is maybe the most obvious, which is just that, the small size required to accommodate these types of wearable products. Here's one example of a pretty recent introduction, the BM55, I believe this is, which won a CES Innovation Award. for what that's worth. I think more interestingly is just to show how small these connectors that we're talking about really are, using a penny as an example. The entire width and length of this little guy here is about equal to Lincoln's ear. And the stack height, if you look down to the bottom in inches, we usually use millimeters, and this would be the entire stack height can be as small as about 0.5 millimeter, which means you could stack 3 mated pairs of these connectors and you'd still be below the thickness of the penny. So again, just to put them in perspective, these are small things that you can almost literally lose in the palm of your hand. Here's more examples of the same type of solutions. All of these are suitable for wearable applications in one form or another. In addition to the small outer dimensions of width and length, another key metric that's important is the pitch, or the distance from one signal pin to the next. And here we are showing examples of some leading edge solutions supporting 0.4 or even 0.35 millimeter pitch. So you might notice the length dimension on our connectors is sometimes missing in our specs, and that's because it's sort of dependent on how many contacts you choose. And most of these connectors are available with a variety of a number of signal pins. And so the length of the connector is going to be the pitch shown here times the number of pins in each of the 2 rows, plus some additional fixed distance for the end cap structures of the connectors themselves. So 0.4 and 0.35 is sort of the leading edge mainstream manufacturing technology. But here on the next slide is some examples of what we're doing to address the pressures to offer even smaller options, where we've recently begun introducing solutions with a even smaller 0.3 millimeter pitch. It is worth noting from a manufacturing perspective, tier 1 contract manufacturers in Asia are generally quite comfortable with the 0.4 and 0.35 millimeter assemblies that I just talked about on the previous slide. When you get down to the 0.3 millimeter, it really is pushing the envelope. And in some cases, it may make sense to stick with a slightly larger pitch, just from a manufacturability standpoint. On the other hand, if you have a need to go even tighter, we are starting to introduce designs with staggered contacts and staggered surface mount solder pads, achieving, for example, effective pitches of 0.175 millimeters on the cable, but with a solder SMT process that still needs to only accommodate 2x that 0.175 millimeter, or again, back to the 0.35 millimeter pitch. So those are something that are an interesting solution if you really have a dense interface connection and you really need to wring as much connectivity as possible in as small a length as possible. And we can share more details on those upcoming staggered solutions upon request. The BM55 product, again, is the 0.35. And on this slide, we also show an important benefit that's sort of become a checkoff requirement by some of our biggest customers because they like it. And that is what we call fully armored mating. And that's adding tiny, metal structures on every surface of both pieces. So in high volume assembly lines, which are often still done manually, there's only metal on metal contact surfaces. There's no metal on plastic, and there's no plastic on plastic. And that greatly reduces the likelihood of damage due to those very small plastic structures. These same metal structures also on many of our series now include small détentes or locking types of cavities in each contact, as well as on the end structures. And those give 2 things. They give a locking effect with better retention force, meaning the connectors are less likely to come apart. And just as importantly, they give a nice tactile confirmation click when mating. Sometimes you're doing blind mating because these connectors are hidden behind a small PC board on one side and behind a larger FPC cable on the other. So the clicking sensation can be quite important as well. Here's a little better view of where you can see those détentes built into the structures, both on the individual signal contacts and down here on the end structures as well. And to compare, here's one of our 0.35 mainstream pitch solutions, the BM29. It's a more general purpose solution, partly due to the fact that it does have more options for pin counts to address a wider range of signaling opportunities within a wearable product. And here's the two side by side just for comparison. You'll find slight differences in addition to the pitch, one being 0.3 and one being 0.35. You'll also see that the height is just slightly different with the BM55. Again, a current best of industry, 0.5 millimeter total stack height for the two pieces mated. The BM29 just a bit taller at 0.6 millimeters. And just like pitch, there are times when having the very smallest stack height may not be the best solution. And a great example of that is you may have other components in close proximity on your PCB that you need that FPC cable to be able to not interfere with when you're routing it in your product. So you may actually want a slightly taller stack height. And we are also starting to introduce many of these series with variable stack height options. So same footprint, same connector spec, but different, in some cases, multiple different stack height options, just to address those types of design concerns. If we move to another microconnector family, the DF40, we've recently introduced another very interesting feature, and that is an active floating feature. It's tooled right into the connector itself, and it's represented here in the DF40F, the last F in the part number denoting the floating functionality. The DF40 has these active floating features structured on one side or one half of the connector piece, the side that we call the plug. And this allows misalignment compensation during mating or after mating up to a full contact pitch. So these two connectors here are, again, a 0.4 millimeter pitch from one signal pin to the next. They can actually be misaligned by up to 0.3 millimeters or almost an entire pitch and still automatically flex on their own and keep and maintain that perfect signal pin to signal pin reliability. So again, these are useful for blind mating when you may have difficulty or your assembler may have difficulty guaranteeing the perfect alignment of the connectors, or for connectors that aren't aligned perfectly by the assembly process of how they're soldered onto the PCBs. And a great example of that is if you have a path where you need multiple connectors between two rigid PCBs, it can be quite hard to guarantee the sub-millimeter precision in how those two separate connectors are positioned. So having a floating mechanism in both of those connectors can greatly relieve the possibility of difficulties during the assembly process. So these floating structures are pretty much geared towards the assembly and manufacturing benefits versus the aftermarket shock and vibration benefits, which could also be a direction you go with floating mechanisms. Here's just a nice little side view. Because we put all the floating mechanisms into one half of the connector, we're able to take advantage of the variable stack heights that already exist within the other half of the DF40 family. As a result, the floating option is available from a 3.5 millimeter total stack height all the way up to a 6 millimeter stack height in increments of 0.5 millimeter, which again, all of these are going to be too big to fit into something like a smart watch, but certainly suitable for a larger wearable application or for a wearable accessory such as a docking station, a charging case. Moving right on, talking about our ZIF connector lineup and going right to one of our very smallest recent introductions, the FH64. Again, this is an industry-leading size form factor down to only 0.5 millimeters in total height. And in addition, the pitch is even more aggressive. In this case, we have used the staggered dual rows of contacts, resulting in an effective signal path pitch of only 0.25 millimeters, again, while leaving the surface mount soldering pitch at a more workable 0.5 millimeter. So if you zoom in, you'd see a sort of a little interleaving of the patterning on the FPC, which mates in turn to staggered or internal dual rows of contacts within the little connector itself. This one does have a manual latch, so it's more of a typical ZIF structure from that standpoint. As I mentioned, we've also introduced a family of ZIF products which do the locking on their own. We call that family our One Action family. And it's sort of easy to see the benefit if we compare it with a conventional product at the top. A conventional product has, again, that mechanical actuator. It needs to be shipped from the factory and stored and brought to your assembly line, all with that actuator open. If it closes without a cable inserted, it can deform the contacts and reduce the retention force. So once it's in your assembly line, your assemblers need to insert the FPC cable, a second step, and a third step is to close that actuator and ensure that the cable is locked in place. With our newer One Action series of products, all that's really taken care of with one step. All you need to do, or your assembler needs to do, is insert that FPC cable, and it's done. That's the end of story. The connector locks itself. And let me show, while I talk a little bit, a quick video of sort of how that works. It's pretty self-explanatory. We've got the little spring actuated locking mechanisms on both sides, left and right, and those latch to an easily tooled notch that your FPC supplier places in the pattern of the flexible printed circuit. Again, the most obvious advantage might be the timing and reduction of up to 3x in the cycle time for your assemblers to perform the insertion of the cable, because it's only one step. As you can see here, or it's just passed, if you do need to replace or remove the cable for rework, you can do that by lifting up the back of the cable. And it's got some other interesting benefits. And probably the most interesting other benefit is a design benefit. For a standard ZIF connector, you need to leave some keep out area around the back and on top of the connector, because during assembly, the assembler needs to have room to reach in there and close that lever after inserting the cable. The One Action series don't need that keep out space because the cable is simply inserted from the front, end of story. So you have suddenly a lot more opportunities to place other components in close proximity to the connector in the X and Y dimension, as well as stack other substrates, PCBs, modules, screens, displays, whatever's on top of your small wearable product on the inside, and not worry about having access to insert that cable connection later in the assembly process. So it's a pretty significant advantage, not only from a cycle time standpoint, but even from a design flexibility standpoint. It's pretty popular. It's grown pretty popular pretty quickly, and we're growing this family of products pretty quickly as well. This isn't everything, but just a few examples of variations that we have with different pitches, different form factors. A lot of these are in a horizontal, typical traditional ZIF horizontal orientation where the cable comes in from the side, but we also are introducing vertically mated One Action solutions where the FPC cable mates at a right angle to the PCB board. The One Action family of products is aimed not just at wearables, but a wide spectrum of consumer electronics products. But again, on the lower end of the smaller size, like that first product I showed, the FH64, very much suitable to even smaller wearable solutions. We also offer our own lineup of I/O connectivity. I talked about micro USB, but showing here our growing family of Type-C solutions. We do a variety of configurations. Again, most of those are going to be a traditional horizontal orientation. We do vertical mount or sometimes flag style USB Type-Cs. We do the horizontal in a top surface mount solderable configuration, a mid mount where you cut a notch out of the edge of your PCB so that the surface plane of the connector is in line with the edge of the PCB. We do ruggedized screw type connections which I think they're great because they really reduce the risk of lifetime wear and corruption of the solder pads. In these cases, they have a threaded screw that actually locks them in place on the PCB. And interestingly, and sort of differentiated from some of our competitors in this market, we're offering a growing collection of water-resistant and waterproof options. In some wearables, that's important as well. So moving right along, another growing and continuing need for wearable product designers is the ability to manage higher and higher power paths in addition and in conjunction with the signal paths within connectors. So let's talk about why that's important and why that's a requirement. Again, using the smartwatch as an example, here's some of the reasons it's important. Displays are getting higher power, higher resolution, even in small wearable products. Wireless connectivity, you're having higher frequency wireless connectivity, you're having multiple wireless radios, even within a small wearable product, adding to the power requirements. The interfaces themselves have their power requirements, and maybe most obviously in the lower left, simply the power paths from your battery to your internal components are requiring the ability to accommodate the full power capability, which can be in the several amps, even for these smaller types of wearables. So let's look at how we're addressing that and how our product line is evolving to increase that capability. 3 amps is already pretty significant for these tiny connectors, and we've grown these from up to 5 and even 10 amps of power. It's sort of interesting to see how we've done that. What we've done is started to repurpose some of the end metal structures on both ends of the connector. These were originally placed for mechanical support, but we've quickly learned that we can repurpose those as additional current carrying capabilities, in addition to adding fat solder pads to maximize the current that can be handled. That's how we've gotten up to 10 amps of power. But even more recently, we've decided to see how far we could take it, again, driven by customers, including wearable customers, to give them as much power handling capability as possible in a similar microstructure. So here you can see one of our newest products, the BM50, where we really shifted and really tried to focus all on power and only threw in this case, 4 signal pins, which likely could be used as something like battery management. So the focus here is giving you a solution which really maximizes that power handling capability, but still in a tiny connector form factor. The width of this is about 1.6 millimeters, and the entire stack height, again, is down to that 0.6 millimeter form factor, perfectly suitable for even smaller wearable solutions. We have another sister product just introduced as well. It has 6 contacts if you're looking for slightly more control signals in addition to the 15 amps of power. But if I was going to leave you with one go-to solution to consider, to start with, it would be back to the BM29. The BM29 does have the power rails repurposed at both ends, supporting up to 3 amps of dedicated power. It does include the same fully armored structures that I already talked about, which your assembler houses will like because it reduces the likelihood of damage during assembly. It also, in addition to the locking détente structures, also includes a 2-point redundant electrical contact. So that's going to be very important too for guaranteeing lifetime impedance and electrical connectivity assurance for the connection itself, which is what a connector is all about, right? It's getting your electrical signals from one place to another. Having 2 points of contact greatly increases the reliability over the lifetime of the product. And the BM29 brings that too. Finally, it's lead-free, halogen-free, so it's ready for prime time today in most design environments. And again, it has a healthy and growing number of pin counts available. And all of these board-to-boards are by nature dual row. So when we say 24 pins, for example, it's 12 upper and 12 lower, which again helps reduce the length of the connector by splitting those number of contacts into 2 rows. And again, all of these connections, numbers of signal pins always include the end cap power rails as well for handling a full 3 amps of forward power and 3 amps of return. So again, if I was going to leave you with a good hybrid, what we call a hybrid connector with both digital signal and power contacts, BM29 for wearables is really a good place to start. So lastly, but also fairly obviously, is a challenge today, which is related to managing higher and more crowded high-frequency signaling paths. Radios and high-frequency signal paths are being added to the smallest CE devices today, and that makes noise. These emissions are coming from things like Bluetooth frequencies up all the way to the latest Wi-Fi standards, and even beyond, in some cases, to 5G, which, as you may know, goes all the way up to millimeter wave or 30 gigahertz and greater frequencies. In addition, even wearables, you're sometimes now finding more than one radio device. Multiple radio paths are being added. And this is going to add to not only the component themselves, but to the circuit trace radiation concerns. These can be internal interference concerns. They can be external interference concerns. They can be a combination of both. And it's not just analog RF that is of concern to our customers, but increasingly these crowded digital high-frequency paths are pushing the product designers to look for better shielded solutions. So the ideal goal, I like to sort of compare it to what a lot of you as designers are certainly recognize, which would be a shield box type of structure. Now that's way too big to put in a smartwatch or an earbud. So the goal that we've been given is try to build something that at least brings something like that effect into the connector itself. So combining really the shield box type of structure into the little tiny micro connector. When we think about it, we could argue we've done something like that all the way back to decades ago in our individual micro coax, which are a shielded cable with a pretty nicely shielded plug and receptacle structure built into them. These products already have supported up to 10 and 15 gigahertz solutions for a long time. But today the interest is more on the board-to-board or board-to-FPC structures. So much more recently, we've started to introduce shielding mechanisms into these small connectors themselves. This first example on the left, we focused on internal interference. It's particularly fixed or next, isolation between separate signal pins. So it's a little hard to see, but what we've done is embedded shielding structures right down the middle of the connector, inserted into the plastic itself through a insert mold process, and greatly relieving the isolation effects by placing one high-frequency signal path on one row and one on the other. Even more interestingly is what we did next, which is in this next connector here, the BM56G, adding an entire external shielding structure, pushing the frequency capability up to even 20 gigahertz. Here's a little better view of that connector, showing the 360-degree metal structures on both pieces. So once these connect, they're sort of nested, one inside the other, adding to some degree a double shield structure even. And again, all within the same, exactly the same small form factor that's expected by our customers for something like a wearable, the 0.6 millimeter total stack height, and something down to the 2 millimeter range for total width of the connector. If you look at a cross section from the side, a cutaway view, you can see through simulations, just visually, a reduction in those external emissions, and same from the top view, where the double shielded structures greatly reduce the radiated emissions that you're going to be experiencing, which can interfere with other componentry on your product. So this shielding is quickly becoming pretty attractive to a lot of our customers. This same BM56G has that same fully armored structure that I've already talked about. It has the same detente click built into the contacts, both at the ends and each individual signal contact as well. And it's also being addressed with a slightly larger connector. I talked about the floating mechanism of the DF40. We've also, just before that, introduced a version of the DF40, which also has a a external shield structure built into the connector. So again, like the BM56, DF40G brings that level of shielding now into a slightly larger form factor. And again, if we looked at the simulations, you see a great reduction qualitatively in the amount of noise that's simply emitted as a result. I should mention these are to optimize the effect. We can work with you to optimize your isolation on your PCB ground via patterns and with your FPC supplier, excuse me, to give similar shielding structures in the FPC. So it sort of all works in concert, and the end result is something similar to that shield box effect. And the DF40 shielded version is available in a variety of stack heights down to 1.5 millimeters. And supports most of the leading high-frequency digital signal protocols today, from USB to MIPI display interface standards. Now, finally, we have a coming product, which wasn't available for public sharing quite yet, but hopefully will be maybe as soon as next month, January. So I can just verbally describe it. It's sort of the best of both worlds from these last two that I just described. It's back in the form factor of the BM56, which again is only a sub-millimeter total stack height, but it's a general purpose product with a wide variety of pin counts like the DF40. And actually, it even brings something better. It brings a even more sophisticated shield structure, which is seamless and flush soldered to the PCB. So it's really, there's no gaps, even at a microscopic level on the shield. And therefore, the resulting performance benefits from that interference and EMI domain is even greater than any of our previous solutions. So ask us about that if that's something that might be of interest, and we can certainly give you more details even before the official public release. We do have additional solutions that support shielding. From the ZIF type of connector, we have multiple families of products that support shielded FPCs or shielded FFCs, which stands for flat flexible cables. We have a larger form factor, again, could be more for an accessory wearable product, shielded device that also includes mechanical active floating mechanisms and also includes high power rails on both ends of the connector. That's the KP27. And as I already mentioned, we do individual discrete microcoax shielded product, but we also have ganged microcoax, both in a 0.4 millimeter fine pitch or even smaller 0.3 millimeter pitch products with a variety of pin counts as well. So what about technical support? That's usually the most important factor, you know, after the sale, if you will, or even during the sale by our customers who are engineers often and want to get as much help as they can in making sure what they're choosing is going to work as best possible in their own design application. So sort of break that down into two categories. What can we point you to find on your own? And what can we do to help you when you still need some human support beyond that? So first of all, where's the resources that you can go to immediately and start to find this type of information? Well, not surprisingly, it would be our website, hirose.com. And it's actually a good place to start. It's got a very simple search bar right at the top of our homepage where you can start to enter and find solutions. On the very same homepage, we've got another menu bar where you can select category, and you can see some of the types of category of connectors I've already introduced and more as well. So if you know the type of connector you're after, you can start here. Conversely, on that very same menu bar, there's another category for application. And there you can see, and for the very first one you can see is smartphones and wearables, where we focus a lot of our attention. So you can click on that and you're going to then get a breakout of lots of different types of connector solutions for lots of those different types of internal connections that we've been talking about. Once you've sort of zeroed in on the type of connector and you know what type of family we call it, you can simply go to that family page, again, from our first search bar, BM28, BM29. And first, best thing that I recommend doing is jumping right to the catalog, which is this button here. The catalog is a pretty useful resource. It's going to give you things like general features that are applied to any of the connectors in that family. It's going to give you more detailed spec sheets, environmental performance, and importantly, it's going to give you the key code, if you will, on how to decipher these little part number extensions and make sure you're focusing on the exact part number that's going to be the best fit for your application. Once you've got that part number in mind, you can now either select it just by going to a list here of all the product numbers within the series, which are mainly just all the different pin counts, or you could just cut and paste that same part number back into our homepage search bar. Either of those paths will take you here to the individual specific product page, where suddenly you're going to see another layer of technical detail that you didn't when you were looking at it from the series perspective. In this case, you're going to be able to download directly things like a 2D drawings, 3D models, either in IGES or STEP format. And we're just now starting to load up standard footprint files as well, which you can download directly either in Allegro or Altium format. You're going to get a little more detailed specs that apply just that particular part, that particular pin count. And you can even go and check what inventory looks like if you need to get something quickly from some of our US distributors. And there's a button there to click and request samples of these products, which we're very good about and very happy to do. If you need some more help beyond that, of course, that's what we're here for. This is the building I work in here in Silicon Valley, California, where I'm very happy to say we've got our own local hire signal integrity engineering team. And they can really roll up their sleeves and work with you on things like PCB analysis, PCB optimization, whether that's things like ground vias, side plating effects, PCB stack-up effects, any of those and more. And just as importantly, our engineers can go beyond just helping you evaluate your PCB landing pattern and connector performance, and really look at entire subsystem performance that might include the connector, the PCB, a cable, maybe even a mating connector on the other end. So we can look at that for things like SI performance, VSWI, insertion loss, and also going back to some of those shielded products, we can, if that's EMI is a concern, we're starting to do more sophisticated modeling with our customers on things like radiated gain and external emissions, and seeing how to optimize that from an overall subsystem standpoint. So let us know. And I should mention, it's not only here in San Jose. We've got an engineering resources at our headquarters in Chicago. And we support with those some of those standard 3D models. I already mentioned IGES and STEP. For our own simulation, we work probably most heavily on ANSYS's HFSS platform. And I should mention that with ANSYS's new HFSS 2023 release, we worked with them, and some of our Hirose connectors are now included in their own component library. So without even leaving the ANSYS environment, you can start to grab some of the Hirose solutions. It's just a few to start with. We'll be working with them to hopefully increase that selection going forward. A lot of our simulation and technical work has been driven by the 5G industry and the consumer electronics space. Again, working all the way up into millimeter wave domains for things like radiated gain. We also have a team and a whole family of products that is focused on backplane, very high frequency server style interconnectivity. And there's a lot of simulation and analysis required for those types of solutions. And they sort of cross over, and we bring that know-how back to the micro world for some of our smaller connectors. So last slide for me here for next steps. We have some larger offices scattered throughout the country. Again, all of these offices I'm showing here have not only sales staff, but engineering staff local. So if you find somebody here that's close to you, it might be a good place to start. Obviously, you can reach out to us directly online, and we'd love to continue the conversation with you and answer any additional questions we can. So with that, let me hand it back to Scott.
Excellent, Mark. Really great job. And I do have a number of questions already kind of queued up. So let me jump right into a couple of those questions. Can you clarify Hirose's definition of armored versus shielded?
Armor versus shield?
Shielded, yes.
Yeah, okay, sure, okay. When I talked about fully armored, that's really a manufacturing benefit, and it's a ruggedization benefit to avoid damage when you are, I should say, your assembler house, right? Whether that's in-house or a CM in Asia is actually putting these things together. I think it's good to remember how tiny these connectors are, right? The overall connectors, half a millimeter in height. So imagine how small some of those substructures are, the walls of the plastic. They're just maybe less than 1/10 of a millimeter in thickness often. So it certainly doesn't take much force to damage, crack that type of plastic. And the fully armored structures are micro metal structures that are placed on top of those small plastic substructures to prevent damage during high volume assembly. So that's the fully armored if that helps. The shielding is a different mechanism, placing metal structures on the outside of the connector primarily, with the end goal being to mitigate EMI concerns. So it's a very different, end result. In some cases, they may overlap, and the outer shield structures may add to that ruggedization of the connector during mating, but they're sort of designed with those two very different end goals in mind.
Okay, perfect, Mark. Thank you. The next question that I have regarding the BM29, does Hirose have life cycle and reliability data versus other manufacturers? Which may be a key way for
side by side versus a name other manufacturer. But yes, we definitely have a lot of lifetime cycling. Some of that's going to be right in those sites that I sort of gave little examples of, right on the catalog and on the individual product. You're going to be able to find environmental data, and often that's going to include mating cycle, testing. But if you don't find as much detail as you're looking for on the product site, the series page, let us know. We almost always have more detailed test reports that we can help provide you. And if you have even beyond that more specific testing questions, sometimes we can work with you and arrange some specific testing at our factories or our design centers to match what it is that you need to do. So yes, we do a lot of testing. We have a voluminous test reports on every one of our series. A lot of that information is available right on the product site, and we have a lot more information behind the scenes if you let us know what you're looking for.
Okay, next question. Can you talk about is there a most popular type of connector in the wearables market? Are board-to-board is most popular? Flex cable, board-to-board. Can you speak to what you see as kind of the most popular utilized connectors in this space?
Okay, I guess I just go back to the two main categories, and they're both used, heavily in wearables. If I had to pick one, I'd say the board to FPC. And that's true across all the consumer electronics devices, just to give you our perspective. Board to FPC is a real go-to solution. It simply, meets the requirements of putting little sub-module boards together, of putting componentized solutions together to mating displays. Although displays, even small displays, that can sort of segue into the other larger category I'd mentioned again, which would be the ZIF, the tiny, small micro ZIF connectors. So it definitely would be between those two that would take up the predominant, number of connections that we see being serviced within wearable type products. And if I had to pick one, I'd just pick the board to FPC because that tends to pop up very often, even for these small form factor products. So those would be the two for sure.
Perfect. I've got a really good one here. The person that asked the question said, we mainly use direct soldering instead of connectors. What kind of merits can you offer with connectors versus kind of leveraging soldering?
Yeah, well, I guess good question. Direct solder is still popular. Certainly, it's cheap, and although from an assembly standpoint, it's not necessarily the cheapest solution. We see it most often used in a power path, maybe from a battery. So, talking about the benefits a connector brings, and we're actually, of course, as a connector supplier, happy to see a lot of the our higher volume wearable and other consumer electronics customers actually moving away from direct solder to connectorized paths for batteries. One simple reason, although not the only one, but one reason would be the design for serviceability trend that a lot of us are seeing in the market, right? There's pressure to allow more aftermarket repairs and replacement of elements within consumer electronics products, and batteries would certainly be one prime example. So having direct soldered obviously makes that a little bit more difficult. Having a cost-effective micro connector in that path makes it eminently, serviceable. Another advantage would be, whether you're designing for serviceability or not, simply in the supply chain and manufacturing chain, you may have your boards manufactured in Singapore and your final assembly done in China, and having a simple connectorized solution to put those different elements of your product together gives you more flexibility on how you're managing your DFM or your design for manufacturability. So those are a couple reasons why having a connector solution is a benefit. I guess one more throw in is that the connector, again, is a hybrid solution. So now you can combine signaling and power path in a single path, where direct soldering becomes a little bit more tenuous or unviable for 36 micro pitched connections. But if you're taking advantage of a micro connector already, you can really do both. You can have your power path serviced right in the same connector solution as is giving you your multiple fine digital signal paths together. And at the same time, you've got the ability to rework the products if you need to, which direct soldering obviously doesn't really allow.
Okay, thank you, Mark. I think that's it for questions. One last thing I'll share.
There was one in the Q&A. Did you get that one?
I did.
Okay, thanks.
Okay. Well, I just would like to thank everyone for attending today's session. We will be reaching out to everyone the sample kit that for attending today's session, and we really appreciate everyone joining us today. Of course, you can always reach out to us directly as well if you have additional questions. But again, thank you for joining today's session.
Great. Thank you, Scott. Thanks, everyone.
I was just going to quickly mention that we do have a wearables page on the Hirose USA website that has a ton of great information. You could just go right on the US site. It's one of the scrolling banners. Thank you for joining us.
Thank you.